So today we will see one problem in approximate methods. We already explained what are the approximate methods. So one is a portal frame. Second is cantilever method. So we already discussed how the portal frame method works. So now I will explain one simple problem in portal frame method. Okay, so take one frame. See, two stories, each one is 4 meters height, so base length 4 meters, 5 meters, again 4 meters, and the transverse loads at this joint is 20 kilonewton, at this joint is 35 kilonewtons. All columns has a equal area. Okay, so how to proceed? First you have to put hinge at the location of center of every beam and column. So hinge means there is no transfer of moment, only a transfer of shear. So find out the shear first in the story shear. So in this first story, see, so in this, so total shear is 20 plus 35. 20 plus 35, it's 55. Total is 55. 55 is resisted by these columns. Okay, 55 is resisted by these columns. So how much it takes by each one? So we already know the simple rule is not equal. So all 4 columns not taken by equal. So the simple rule is inner columns takes 2 times the outer column. So that means if you call it as in this is an x, this is 2x, this is 2x. Okay, so now comes to the total. 2 2 1 1 6x equal to total is 55. So each one is 55 by 6. How much it is? 55 divided by 6 is 9.16. 9.167. You can call it as 9.17. So this is 9.16. This is 8.3. This is 8.3. This is 9.16. Okay. Now the same logic applies to this top story. So top story, you can write down the free body. If you see the free body, if you see it is a free body, this is a 20. This is resisted by this story shear. That's it now. If you put a hinge, see the hinge, this is the hinge. There is only transfer of shear only. There is no transfer of moment. So if you consider this is only shear transfer. Same logic applies here. This logic is applies here. How much each one is takes? 20 divided by 6. That's it now. 20 divided by 6. 3.33. So this is 3.33, this is 6.66, this is 6.66, this is 6.66. Okay, so I will write here. I will write here. So this is this 3.33, 6.66, 6.66, 3.33. Shear, if you draw a free body like this, it will comes to like this. Here, if you take here, exactly this is equal to this value, because you see it's a shear transfer. This value must be equal to this value. If you cut free body na, those two must be equal na. So no need again. So this value is C 9.16. This value is 18.3, 18.3, 9.16. Once you draw the story shear, now we can calculate the bending moments in the beams, columns, axial forces, in everything. So for that, you need to draw free body diagrams. I will draw free body diagrams, and how to calculate those things I will explain later. Now only. Okay. So draw free body diagrams. Each one you can draw. You can draw. Free body. Cut the joints. Cut the joints. So write down the shear. Write down the shear. This is a hinge. That's why only shear. There is no moment if you cut it. So write down the values. It's a 3.33, 6.66, 6.66, 3.33. Here 9.16, 18.3, 18.3, 18.3, 9.16. So maybe you can write it like this. This is 9.16. This is 9.16. You can write like this only. This is a 9.66. This is 9.16. Cut the free. This is cut. Cut it. Cut it. You can balance the transverse load. Shear. That's only na. So you can write down 18.3, 18.3, 9.16. Here also 3.33, 3.33, 6.66, 6.66, 6.66, 3.33, 3.33. Okay, so now comes to the first thing. I will write down here. First, bending moment in columns. Bending moment in columns. First, see this column. See this column. What is the bending moment here? Bending moment at this location. So this is the load and this is the distance. What is the distance? What is the distance? C is 4 meters. So half of the distance is exactly half of the distance is 2. So see, this is, it look like a cantilever. If you just feel it is, this is the load of 3.33. This is a joint bending moment. Here is the bending moment. There is no bending moment here. Just imagine it's a cantilever. We already explained the previous class. No? So what is the moment and what is the direction? The moment will come. This thing. This moment is 6.66. So here, just see this moment. What is the moment direction? You can easily take it anti-clockwise. What is that value? 6.66. That's it, na? There is no moment here. You don't confuse this is the force and this is the moment. No, no, not confuse. This is the force. This is the giant has a bending moment. There is no bending moment here. That is a hinge. Why we assume hinge in between column and beam? We already explained the previous class and introduction class. Okay, so that's it. So now comes to what is the moment here? 6.66 and it's a height of 2. So double. What is that value? 6.66 into multiply with 2. 13.33. 13.33. 13.33. Here 6.66. What is the moment here? It's also giant, has a moment. So which direction? See, this is a cantilever. Assume is a cantilever. This is the force. This is the giant. Assume it is. Moment is in direction anti-clockwise only. So what is that value? Again 6.66. 13.33. 13.33. 6.66. So now comes to the ground story. What is the moment here? 9.16 multiplied with distance is, again it's a 4 meter, half of the distance is 2. So 18.3. That's it now. 18.3. So here 1836.6. So here 36.6. Here 18.3. So here say, so force is, this is the force, this is the distance. Have you understood? Yes, I think you understood. So here also it's a 18.3. Here also 36.6. Here also 36.6. Here also 18.3. Now bending moment in columns is over. Now comes to the second element, bending moment in columns. Gee, beams. What is it? Bending moment in beams by equilibrium only. There is no required of extra equations. By just an equilibrium. How can we will change the color? So it is a giant. It is a giant. 36.66 in anti-clockwise. So giant, we cut the giant for the free body diagram of this beam and this column. So what is the bending moment towards beam? Should maintain a giant equilibrium, na? Should maintain a giant equilibrium. The sum of the moments in the giant is should be equal to 0. Moment, not a bending moment. Moment is 0. Bending moment has 6.66. Moment is 0. If you cut that, okay, you know, I think you know the difference between moment and bending moment. Okay, so this is a anti-clockwise, so must be it's a clockwise of 6.66. So what is the moment here? Same, the moment is here also. The moment is here also, clockwise 6.66. See, this is clockwise, anti-clockwise. This is anti-clockwise. This should be this is an anti-clockwise. That should be a clockwise. So, wrong. Okay, this, see, this is an, okay, wait 1 minute. That's an anti-clockwise. So this must be a clockwise. This is value. This value is 6.66. So here also it's a clockwise 6.6. Why it is the same value here and here? Why it is same value here and same direction also, same clockwise? Because we assume, previously we assume point of contraflex at the center of the column also. We explained in the previous class. I explained in the previous class. If the point of contraflex at the center means both sides has a moment is the same moment, then only The center has a point of contraflexure. The it's a one thing. This value is sagging. This value is hogging. If you draw a bending moment diagram, the bending moment diagram passes through its center. It passes through 0. That's the point of contraflexure. We already know. If you assume a point of contraflexure at the center, must be have both side has the same bending moment and same direction. Same direction means one hogging, one sagging. We already explained. No need to explain once again. So how we arrive that moment, that's the only I want to explain it. Okay. So the working now comes to see. So what is the moment here? So again equilibrium. This is 6.66 clockwise, 13.33 anti-clockwise. So maintain a giant equilibrium. How much it is? Again it's clockwise 6.66. So if it is clockwise 6 point, it's also clockwise 6.66. Again what is here? 6.66. It is a clockwise 6.66. You can check here. It's anti-clockwise of 6.66. It's a clockwise of 6.66. It's good. There is no error. See, it is every column has same bending moment. This side and that side, right side and left side. Okay, and also all columns has same moment. We'll see next story. Next story. See, in a single floor, all columns has same bending moments. See, all beams has same bending moment. I will show you. So here, you see it. It has a point of contraflexure. Bending moment. What is it here? 6.66 in anti-clockwise. 18.3 is also anti-clockwise. Okay, 18.3 anti-clockwise and 6.66 also anti-clockwise. So what is that moment here? 24.96. So why it is 96? I will mention as 25. Okay, I will mention as a 25. I will use green ink only because all columns bending moment I will use green. It is 25. So once it is 25, it's also 25. Okay. Now comes to the here. What is that value? Is 25 in clockwise direction, 36.66 anti-clockwise, 13.33 anti-clockwise, 13.33 anti-clockwise, plus 36.6 anti-clockwise, 25 is in clockwise. What is the difference between those things? Again it's 25. Okay, 25 clockwise. I said every column in a story level has same bending moment either side and throughout the story. It's 25. It will come stay as a 25. Here also comes 25. Here also comes 25. See, 6.66 and 18.3. 3, 4. You can call it as like. No need to talk. Take an approximate. It's approximate methods. No? 25, 25. It's now over. Now bending moment in beams also over. Now comes to the third. Now comes to the top. Shear. Shear in column. Shear in column. I will explain this column. So this is the column, free body. What is the bending moments here? This is 6.66. Here 6.66. So you can put shear. That's something weak. So write down equilibrium equation. What is this length? This length is span length. 4. This is a 4. This is 5. This is 4. You can write this 4. So V multiply with 4 minus 6.66 minus 6.66 equal to 0. That's it now. So what is the V? 6.66 and plus 6.66. That's a 13.33. So 13.33 divided by 4. So what is that value? 13.33 divided by 4. 3.33. So this is a 3.33. If this is 3.33, there is no vertical load on the span, then compulsory must be this is an opposite direction. This is a 3.33. Should maintain equilibrium. Na? There is no another alternative. There is no another gravity load on that column. Okay, so that's it. This is 3.33, this is 3.33. You can write it some different color. I will use the some different color. So 3.33, 3.33 only. Okay, 3.33, this is 3.33. Again here same 6.66, 6.66. Column beam has height of 5 meters. Okay, 5 meters. Write down how it is. 13.33 divided by 5, so 2.66. So how it is come here? 2.66, 2.66. Here again it's length of 4, span length, so again it's 3.33, again it's 3.33. Comes to here 25, 25. 50 divided by 50 divided by 4, 50 divided by 4, it's 12.5. Here 12.5. Here 50 divided by 5, it's 10, 10, 10. Here again 12.5. That's it. That's it. That means if you draw a free bodies in the columns, its center has a point of counterplexure. There is no transfer of bending moment, only shear. You can draw like this is 3.33, here 3.33. It's a 3.33. You can draw like this, but no need at all. So similar for what is similar to column. Similar to column, you can draw it as a 3.33. It's a 3.33. It's a 3.33. It's exactly symmetry. If you observe these two, symmetry means the procedure is same. The visibility of shear, bending moment, and calculation, everything is similar. No difference between column and bending, column and beam. That's the only I want to express. I want to give a clarity. Okay, no need to draw like this in every beam. Okay, but just understand. That's it. It's over now. It's over. Now comes to the extra axial force in column. Axial force in column. I will show you in different color. We'll try. What's the color? What's the color? Mhm. Mm. Mhm. Okay, I will show you green color. See, equilibrium of joint. It's a 3.33. It's a 3.33. It's a 3.33. Should be joint equilibrium. Consider this is a. Okay, I will show you some. Consider this giant. See, what I did. Mm, okay. What I did. See, just see it. Mm, it's a 3.33. Maintain a giant equilibrium. So this should be also 3.33. That's it. Now this is comes to a bottom side. So this comes to a bottom side. This must be a upward side. So So this must be comes to a upward side. How much it is? 3.3 only. Okay, it's a 3.3. So now comes to the this joint. This joint. See, for this column only, you can just this column equilibrium. This must be a, this is a 3.33 upwards. To maintain an equilibrium of that column, this must be a 3.33. Then only the column is in equilibrium. Otherwise, it's in a kinematic equilibrium. Okay, that must be a 3.33. So now comes to the this column joint. This joint. This is a 3.33. This is again what is that? 12.5. So to maintain a joint equilibrium, this must be a, this must be, see again, this must be how much? 3.33, 12.5, 15, 15.83. That's it now, 15.83. So to maintain a column, total column is in equilibrium, this must be 15.83. That's it. That's it. Now comes to the this joint. This joint. Okay. This is a 3.33. This is 2.66. What is the difference? One is in upwards, one is in downwards. 3.33 minus 2.66, 0.67. To maintain equilibrium, this must be bottom. What is that value? 0.67. So to maintain the equilibrium of the total column, this must be a 0.67. That's it. So joint equilibrium, you see this is a 12.5 topwards, 0.767, 12.5 topwards, 0.67 topwards. This 10 is downwards. So bottom is how much? 3.17. So this must be 3.17. Total column is in equilibrium. Okay. So now comes to the this joint. Okay. So 2.66, 3.66. So again same thing. So how it is? It must be 2.66 and 3.33. How can it balance? Say exactly it's topwards. Topwards, how much it is? 0.67. Then only its balance is the 3.33. That's it. Then it's, so here it comes to the 0.67 downwards. Okay. Okay, exactly symmetrical, not a symmetric, mirror image. Here it comes to this mirror image, here it comes to mirror image here. Okay, so again this much, what is this much value? Is a 10 upward, 12.5 downwards, 0.67 is downwards. So you must it calculate 3.17. So this is 3.17. So here comes to this, here comes to what is this? Downwards of 3.33. Here comes 3.33. Here comes 3.33 downwards, 12.95 upwards. Or what is it? Downwards, sorry. Okay. So this must be downwards, means this is upwards. 3.33. So 12.5, 3.33. So downwards is how much it is? 15.83. Here it's 15.83. Okay, that's it. General C, it's a 15.83 downwards, 3.817 upwards, 3.17 downwards, 15.8 C upwards. So this balanced by this this balanced by this total upward, total vertical force is 0 because there is no vertical force on the frame, there is no gravitational force on this frame. So total vertical forces at the supports must be equal to 0. But one thing I will explain it. I want to inform you that in general, one, if you see this column, this column has a upward force up, this is also a downward force. That means the column is in tension, the column is in tension. Here if you see this thing, the column is in compression, because you see this is the downwards, this is this direction, this means this column is in compressed by these two forces. Again if you see here, it means it's in tension. Here if you observe it, it's a compression. In general calculations, if you observe it, if you throw down any simple frame like this goes like this, it will go like this, it will go like this. It must be in tension, it must be in compression. Are understood? Okay, but somewhere this is in tension, this is in compression, somewhere up to, if you draw like this, if you draw like this, if you throw down some forces, this must be in tension, this must be in compression, but somewhere in center, maybe here or here or here, the tension shifted to compression. So that means if it is in tension, maybe it's compression, maybe it's compression, maybe it's compression. Otherwise, based on the portal frame sizes and heights, bay heights is based on, maybe it's a tension, it's a tension, it's a compression, it's a compression. Because somewhere the point tension shifted to compression, some portion is in compression, some portion is in tension. It is a normal criteria. But if you see this problem, it is the first problem is in tension, last is compression, okay, but here it changes to compression, again it changes to tension. This is not possible to, it's not possible. So somewhere here it's tension to compression, change the point, but it's in compression, this also should maintain a compression, this is also should be in this is must be in compression, okay, some in between the point the tension changes to compression. This is not acceptable, this is not acceptable. In reality it's not acceptable. Once it changes to compression, again next column also is in compression, because just to see the see just see this portion, somewhere this point, this portion is in compression portion, this portion is in tension portion. We already explained in the cantilever method. So some part is in compression, some part is in tension. So but it's like it's just some section is in compression, some section is in tension, but this part is in compression, this part is in tension, this part again compression, this part is in again tension. It's not possible. But here the problem we got this, I don't understand. But looks like the calculations are correct, looks like the calculations are correct, but reality this is not acceptable. In reality this is not acceptable. Are understood? In reality these are not acceptable. So okay, must we will complete the problem. So, last one thing, axial force in beam, axial force in beam. Okay, axial force in beam. See, I will use another color. So, okay, I will use red color. See here, what is the value? 20. So 20 force in the joint. If you see, observe it, it's a 3.33, it's a 3.33 it erased it. So the total force in the joint is 20. we already has a force of 3.33. What is the remaining one? Remaining value 16.66. This is 16.66. So to maintain the equilibrium of the beam hole, not a joint, beam hole, this is must be in 16.66. That means this is 16.66 compression. If it is 16.66, this value is 6.66. To maintain a joint equilibrium, this must be 10. This must be a 10. So that's 10 in compression. So see, this is 10, this is 6.66. What is the remaining value? Joint equilibrium 3.33. So this is 3.33 compression. Again, this is 3.33. So see, joint equilibrium is at this is 3.33, yellow color. See, 3.33. To maintain the equilibrium, yes, exactly what we did is correct. You can check here. So now comes to this joint. What is the giant force? 35 is the giant force. See, what are the forces here in joint? In joint, this is a 3.33. This is 9.66. Just check the joint. Check the joint. This is the 3.33, 6.66, 6.66. Plus 3.33. Here is 9.16. What is the force? Force must be 35 in this direction. Okay. What are the forces? What are the effective force that at the joint? 9.16 minus 3.33. What is that? 5.83. Yes. 5.83 force is an effective minus 35. So 29.17. Okay. So remaining force is 29.17. So 29.17 here. So if you check this now, 25.17 plus 9.16 minus 3.33, you can get 35. This is not 35 should maintain at the joint. Remaining joints has 0, 0, 0, 0. Okay, equilibrium. So this is the 29.17. This is also 29.17. Okay. So again, if you see what are the forces, this is a 29.17. 29.17 plus again this is 6.66. What is 6.66 minus 18.3? It's 17.5. See, 18.3, 6.66, 29.17. What is the effective force now? Here 17.53. Here also 17.53. 17.53, 6.66 minus 18.3. So 5.89. This is 5.89 here. Here also 5.89 to maintain an equilibrium of that beam. So you can check it is 3.33 minus 9.16. You can get 5.83. 89. Maybe not variable. Okay, that's it. So one thing I should remember it. All beams must be in compression. There is no chance to beams enter into a tension. There is no chance. Okay, all beams must have compressive force only. If you check this portion, the beam is in compression only. If you just check it is this direction also. If you throw down like a force here to the joint, so this column may be tension, this column may be compression, but this must be is in compression. There's a compressed. This force is in like this force is in must. It must be is in compression. So there is no chance to enter a beam into a tensile force. Okay, understood? That's it. Everything is over. Now see, bending moment in columns, bending moment in beams, shear in column, axial force in column, axial force in beam. Shear in column, first we entered this is a shear in column. This is shear in column. That's the thing. Shear in columns. Okay, shear in columns, bending moment in column, bending moment in beam, shear in column, axial force in column, axial force in beam. That's it. The whole problem is okay. That's it. So now you can draw bending moments. Simple. So bending moment, this thing. Bending moments. Why I draw like this? Because it has a point. It is a point of contraflexion. Okay, it is a point of contraflexion. It is a point of contraflexion. Okay. So you see the bending moment here. What is the bending moment? 3.33. 6.6. What is the bending moment here? 6.66. 6.66. So 13.33, 13.33. This is the value. 6.66. This is 13.33. 13.33, 6.66. Both are in the same direction. That means one in hogging, one in sagging. Here also. Here also. The value is different, but the diagram looks like here. And columns, beams also same thing. Beams I will draw like this. This is point of contraflexion. Here, like this. Okay. Okay. So why I drag this? Again same thing. See the 6.66, 6.66, 6.6.6. It's a 25, 25, 25, 25. So 6.66, here 6.6. Both are in the same direction. That means one is in hogging, one is in sagging. Once again I will show. So this is 6.66, this is 6.66. Both are in clockwise. That means this is in hogging moment, this is sagging moment. Both are same value, then it comes to the center of point of contraflexion at center. That's it now. 6.66, this 0.6. So bending moment diagrams are over. So shear you can see this is a 3.33, 6.66. Here 9.16. Shear diagrams, how can you draw shear diagrams? Just you can draw 3.33. Here you can draw 6.66. Here you can draw 6.66. Here you can draw 3.33. Here you can draw 9 point. Here you can draw 18 point. It's 18 point. It's 18 point. That's it. Here shear 3.33, 2.66. B 3.33, 2.66, again 3.33. Okay. Here 12.5, 12.5, 10. 12.5, 10. Again it's 12.5. That's it. Axial force, no need to draw axial force diagram. You can mention here on the top of that free top in the free body diagram. Then it's over. Now it's over. But it's the exceptional case. It's as an exceptional case because in general it will come once it's a tension, it's a compression. In between those two, up to this also should be is in tension. This may be in compression to enter into this compression. But this looks like this is some exceptional calculated, not a calculation problem, some approximate method problem. Method calculation wise it's correct, no error. We can observe it, no error in the calculations, no error in the calculations, but the method not describe exactly what is the real view. It may goes to error because it's a approximate method. Na? So this type of problem, exactly symmetrical problem, you see this is 4 5 4, these heights are exactly symmetrical. That's the problem. Maybe this portal frame method not describe what is a real situation. Hmm? But the calculation wise this is okay. Okay, okay, that's it. It's good. So again next I will put a problem of cantilever method next session. This is a portal frame method. Every problem you can do like this only, not much change. May increase base or may increase stories, but the way we are doing the problem is same like this one. Okay, now I will close.